Welcome to APEC. It's February 12th, and I'm your moderator, Tim Ventura. I'd like to thank everyone for joining us on this call, along with everyone watching us on YouTube. In today's session, we're proud to present presentations by Dr. Fabrizio Pinto on the Casimir Effect, Mike Melia on inertial propulsion, Michael McDonnough on plasma vortex propulsion, and Mike Gamble on differential CMG gyro operation. Mark Sokol and Falcon Space will provide lab updates for us, and we'll be finishing off the event with an open discussion and ad hoc presentations by conference attendees. So a couple of quick reminders: you can view conference replays, details, and speaker info on our website at www.altpropulsion.com. Please save your questions for the Q&A session after each presentation. You can raise your hand in Zoom using Option Y on Mac or Alt-Y on Windows. You can also type those questions into chat, and we will go through them after each presenter finishes. So I would like to introduce you now to our first guest. Dr. Fabrizio Pinto is an assistant professor in the Department of Aerospace Engineering in the Izmir University of Economics in Izmir, Turkey, where he founded the EcoSpace Center for Research on Artificial Satellites, and he's an advisor to the Turkish Space Agency. He pursues research in the application of dispersion forces, such as the Casimir and van der Waals forces, to novel technologies on the nanoscale with target applications in next-generation spacecraft. He joins us today to discuss the Casimir Effect, fact, fiction, and applications in space. Without any further adu, let's welcome Fabrizio to today's event, and I will hand things over to him to get started.
All right, tell me that you can see the screen, please. Are we on?
Yeah,
with
yeah,
that screen,
and
great.
you look great. You look great.
Thank you so much. So do you, Tim. Very good to see you again. It's been a few years, so I'm very happy to be here. And thank you for the gracious invitation and the introduction, and welcome to all guests from around the world. And I thought to just back up to the last slide before I go to the first one, and which will be this slide here, so that you can see the Bay of Izmir on a good day, like today. And I am speaking to you from the western coast of Anatolia, the city of Homer, and it goes back 10,000 years. And I have ruins going back to the period of the city of Troy, a kilometer from my house. It's a fantastic area for those of you who are interested in archaeology. And I also would like to welcome my students, or some of them who are here tonight, during the break between the two semesters, because obviously we are on a different schedule. And I will get right into the topic of this discussion. Obviously, Tim will remember we had a related interview years ago in Albuquerque, I believe. And it was a very interesting time for Casimir Effect research. And so it's also time for me to look at it in perspective now, about a decade later, so that we understand where we are. And that's part of the reason that I gave the title, the word fiction in it, so that we all understand what we have learned in the last decade and what we have not seen and what we can see in the future. So there is a tone of realism here, and not so much if you want, some of the hopes that we had at the time. On the other hand, some other hopes had become realized. So I would like to offer a combination of the two. And so getting right into it, here there is a map, if you want, that shows on the left side some of the main fields, if you want, of modern physics, from classical mechanics down to classical electrodynamics, thermodynamics, statistical mechanics, quantum electrodynamics, general relativity, numerical methods, etc. And this is to be, if you want, intersected as time goes by, with developments that you can see at the top, hoping that it is kind of readable, but there are critical issues, there are known effects, and there are demonstrations, and finally some of the goals that we have with the Casimir Effect. It's a complicated map, so I didn't connect everything to everything. Otherwise, it would have been simply unreadable. This is, by the way, the type of map that Mark Millis has introduced in his study of all technologies that may have to do with advanced propulsion. So I kind of took it from him to adapt it, if you want, as a tool. And if you go to the far right, you can see where we are trying to go with the Casimir effect and all the promises that it holds. Grappling, sensing, imaging, communications, stiction, remediation, nanorobotics, energy storage, energy conversion, levitation, and propulsion. And so this may appear to be it may appear to be disappointing, because at some point we were talking about propellantless propulsion, and we were talking about near speed of light propulsion. I would like to take it back into realism. However, I think that you can realize that if we could have industries in all of these subjects that I have, 10 here on the far right, that would be a major accomplishment in the world of breakthrough industry. So I will walk you through how we can get there by keeping it to the physics that we know is correct instead of introducing any new physics fundamentally. I will also talk briefly about some of the open questions, if you want. So let's first talk about the things that are clear. So this is the Urla, the little harbor where I live, at the breakwaters here at the waterfront on a stormy day. You can look at the cloud, the little droplets of water. If you zoom in and get closer, you can get closer to the droplets of water. And if you can get closer still, we realize as we get closer and closer that matter is made of particles. This was where we live here, the ancient Greek city of Clazomene. Anaxagoras came from here, and in 499 BC, the story has it, he brought philosophy to Athens. Athens did not invent philosophy, comes from this town. We don't know if Anaxagoras came from here as an accomplice to the Persians, as he was later accused to be, or as escaping from them. But as we all know, from the western coast of Anatolia and also from Thrace, we have the development of the atomic theory. And this is a huge subject. Any of these many slides I'm going to show could be a presentation by itself. So, in what way does atomism connect to Casimir forces, you might ask? Well, the reason is that typically atomism is considered as a reductionist explanation of the universe, in which we say there is atoms, there is the void, and there is nothing else. Well, modern physics has taught us that this is not possible, that if we had atoms and the void and nothing else, the atoms couldn't interact. And if they cannot interact, we don't have atomism. So the bottom line here is that atomism, in the sense that some people interpret it to be, is insufficient. You need to have more to it than that. And that means, obviously, what we're talking about are fields. That's what we call fields today. The void doesn't even exist. And this is something that Wheeler stated very clearly. So although it's very popular to state that atomism has been successful in explaining the history of the universe, if you want, and the evolution of the universe based on the evolution of its aggregate parts, that's what reductionism would be. It's actually incorrect to state it that way, because the fields are the ones that make possible for the atoms to interact. Now, I would like to say that the subject is even more complicated, because obviously, if we go down the physics road, when we say that these parts are interacting, we need to decide whether we're going to do this classically or quantum mechanically, as we will discuss next. I would also like to state, I know that some of you here in the audience are interested in the philosophy of science, that atomism comes in two different, if you want, subfields or flavors. There is physics atomism, in which the atoms are actually what we would call atoms today in the physics sense. But atomism can also be a philosophical concept in which we imagine that the universe is logically atomistic, not necessarily identifying the atoms with the physics structures that we identify as atoms today. So it's more complex than people would like it to be. And sometimes I am disturbed when I see philosophical atomism confused with the physics atomism. But Lucretius is the one, the Roman philosopher from my hometown, that gave us the most beautiful description of atoms interacting. So if you want, Lucretius gave atomism a poetic representation. It comes, however, from earlier than Lucretius. Epicurus here, talking about writing to in a letter that he receives, that he wrote to Herodotus, not the historian Herodotus, but another one. He describes the entanglement, if you want. This is the best that we can do in English, between different atoms. I mean, the thing here is that if we don't have a way for the atoms to interact, it's completely useless as a theory of atomism. Atomism only works if the atoms are interacting. So the philosophers of this particular, what we call pre-Socratic philosophers of this area, analyzing this particular subject, and I would like to state that Epicurus is not pre-Socratic, but he's the one that re-elaborated pre-Socratic philosophy later after Socrates. But they were wondering how this interaction among atoms could possibly happen at a time that, of course, they had nothing in their hands that we could use to measure or even detect the existence of atoms. So they came up with anything like hooks, basically, and irregular shapes, anything that could allow these atoms to interact. There is a deep philosophical issue in that if the atoms merge, then there is a problem of consistency. If they don't, then the question is, how are they interacting at a distance? So it's a very long and complicated conversation about how the Greek philosophers implemented the interaction of atoms while having vacuum and not having action at a distance. So this was a very complicated subject that actually remains very critical even today. And the reason, of course, that they got to the point that they wanted to have atomism implemented was that, on the other hand, there was the complete denial by the Eleatic school of the universe as changing. So in their philosophy, nothing changes in the universe. And change only happens because our senses are imperfect. So this is a response to that, in that change is real and it's due to these minute, indivisible units called the atoms. So Lucretius gives this poetic aspect, and it's kind of a complex question here, what he meant by the atoms bearing down. That's called the klinamen in Greek. It is basically, imagine these atoms falling through the void towards what obviously wouldn't make sense to us today. But if they don't have interaction, they would be falling in parallel to each other. There wouldn't be any interaction. So once again, we have the appearance of the concept of hooks. Keep in mind that the De Rerum Natura here was a poem. So here in this poem, Lucretius, in a way, attacks the existence of the gods, but mostly he attacks the existence of established religion. People want to say that Lucretius was atheist, but he starts the poem by invoking the goddess Aphrodite. So that wasn't a very good denial of the existence of the gods, if that had been the case. So it's obviously, again, a more complicated subject, as I told you before. Now, a long time elapsed after the purely philosophical view of the existence of atoms. And this takes us to if you want, the scientific revolution here. Galileo, writing about the existence of droplets of water, and that's what I used to start this talk, says that he doesn't know why they exist, why droplets of water exist. Why do we have droplets of water? Why does water appears in spherical drops? And notice that he makes a mistake here. He states that it is not owing to any internal tenacity, but it must be due to an external cause. Well, we know that this is wrong today because it is actually due to internal forces. So Galileo was grappling with a very good question, though. How do the atoms interact if they exist? I mean, why does matter aggregate? Now, Newton was probably the most outspoken self-critic on the issue of intermolecular forces and interatomic forces. Keep in mind that the issue of atomism was quickly perceived, even in antiquity, as I said before, denying the existence of an external force purely connected to the action that atoms exert on each other. So that what I'm trying to say is that there would be God acting and imposing his action on the evolution of the universe. So atomism was interpreted, although it doesn't have to be, as we will see later, but atomism was quickly interpreted by some as a heresy. And so in the context of Christianity, and as you know, Newton was a very believing man. He was very, very attached to his own religion in England at the time. Newton actually mentions the word atomism, I believe, twice in his entire career. He stayed away from it. And at the time, the idea was that atomism is a despicable concept. However, he talks about atoms because they need to, he believed in the existence of nature being organized by, in micro, if you want, minute particles, let's put it in that way. And then the question is, how do they interact with each other? So notice here, in probably what one could argue is the greatest physics book ever written, the Principia Mathematica, Philosophia Naturalis Principia Mathematica. In the preface, Newton confesses ignorance. We philosophers have either attempted to search the search of nature in vain. He doesn't know why and how atoms interact with each other. I find that this preface is a spectacular manifestation of Newton's unending curiosity. He could have sang his own praise and nobody could have stopped him. Whereas in the preface, he talks about something that he has not found instead of finding what he has found, instead of declaring what he has found. It is quite remarkable to me that Newton would admit to this. I have seen editions of the Principia, including the one by Stephen Hawking, in which the preface is not present. It is, of course, a great praise to Newton to state that he is the author of everything that we hold dear today, in a way. But by eliminating the preface, we are eliminating the questions that Newton saw still open in his day. Let's not forget that he admitted to not understanding the reason for the existence of interatomic forces. I would like to say that even before Newton, the issue of how and why matter aggregates puzzled scientists. As you know, in the area of the world where I live, let's call it in the broader sense, the Middle East, saw a rebirth of science after the end of the Roman Empire. And probably the most famous of these scientists for what we care about today was Al-Khazini, who was a Greek-speaking slave of a man by the name of Kazan, and wrote in Arabic, in what at the time would have been under Persian influence, in the book of the Balance of Wisdom. And he talks about what we call the water balance, in which a small amount of water needs to flow through a channel. And he openly states that at some point, the water will not flow due to capillary action. And of course, capillary action is a manifestation of interatomic forces. So this was in translation by Khanikov, who was an ambassador, Russian ambassador to Persia in the late 1800s, and the editor of this very well known book of the Balance of Wisdom in translation. Now, as the revolution, the scientific revolution progressed in the West, the issue of the existence of the vacuum became quite critical. We find here a book by the continuation of new experiments by none other than Robert Boyle, in which he draws this picture that I've seen actually in a book by Sparney on early experiments on Casimir forces, because you cannot look at this figure without recognizing modern day experiments on Casimir forces. Here you have the vacuum chamber, that spherical jar with these, if you want, feed-throughs, we would call them today, with these little strings. And then you have at the bottom marble plates. And the figure is meant to show that you can lower one of these little discs to the bottom of the jar in a vacuum, and then touch a disc at the bottom of the jar. And then when you pull the string, the disc that was at the bottom will remain attached to the disc attached to the string by some mysterious force. Now, keep in mind that Robert Boyle was extremely disturbed by this, because what he wanted to prove was that interatomic forces are nothing but a manifestation of atmospheric pressure. It bothered him that in the vacuum, these forces would exist. Consequently, in order to prove that his own experiment was wrong, what he did, he attached a weight that you can see here at the bottom of the lower disk. He attached a small weight trying to cause the two to come apart from each other, because he was disturbed at the concept that these two disks would adhere so strongly and they wouldn't come off of each other. So eventually he disposed of this experiment and didn't pursue it anymore, believing that he had made a mistake. This is something that we've seen in the history and philosophy of science. You know, science, even Michelson believed that his own experiment wasn't accurate enough or good enough. So what I'm trying to tell you is this, that interatomic forces have been known since antiquity. And these sophisticated experiments, I mean, this is, you know, manifestation of macroscopic forces between highly polished marble slabs in a vacuum. You could publish a paper about that today, and that was done in the 1600s. Now, Feynman, a very little-cited paragraph of the Lectures on Physics, talks about a more modern way to demonstrate van der Waals forces. And it is in the Lectures on Physics. And he, although he misspells the word Johansson in that paragraph, he talks about the Johansson blocks. Now, I don't know how many engineers know about Johansson blocks even today. It is not as common to see them around, but they are still used today. And they are basically extremely accurately machined parallelepipeds that can be attached to each other to create lengths of any combination. It's like, imagine Legos, okay? You attach the Legos, and as you attach the Legos to each other, you can make lengths of different lengths. And those lengths are very accurate because the blocks themselves are extremely accurately machined. And this wouldn't be itself very useful, except for the fact that Johansson discovered at the end of the 1800s that these blocks, when they are very accurately, very specularly polished, adhere to each other by a mysterious force. So the Johansson blocks, you can find them today. They're sold still today. They, there is a way to, if you want, slip them onto one another in a way that they become, that they adhere to each other. And Johansson discovered that himself randomly, because two of these things had become attached. And after a few months that he wasn't separating them, he could have made them come apart even with a hammer. So Feynman, remember, Feynman was a theoretical physicist, wasn't he? And yet he's talking about the Johansson blocks as a demonstration of the existence of van der Waals forces that are very strong. Okay, this is Mr. Johansson demonstrating the Johansson blocks at the end of the 1800s, early 1900s, actually, I believe. By the way, this was done because in Sweden, he set up a rifle making company, and he was making highly accurate rifles of, you know, if you want, next generation. And he discovered that it would have been impossible to do this on an industrial scale if he had had to be distributing gauges to every workstation. Whereas these blocks were fantastic, very speedy, very expedient, and very accurate. You can buy them today. Now, I would like to contrast this, and this is one of the important subjects of this talk, is a very common word that you're going to see when you hear about the word Casimir force and van der Waals force. The Casimir force is very small. The van der Waals force is very weak. I would like to explain a little bit of the vocabulary here. When I say van der Waals force or Casimir force, I'm using them at this time as synonyms, and most experts in the field do the same. Technically speaking, the van der Waals force is a force between two objects in the so-called unretarded regime. That is, when the propagation of light plays the finite speed of light plays no role in the interaction of two atoms. If instead the two boundaries are far enough that the speed of light matters, then it's called the retarded interaction, and that's the Casimir force. Some of you may be surprised to know that if you are over 100 nanometers of distance, the fact that the speed of light is finite is enough to introduce retardation. So technically speaking, we should use the word Casimir force at that point, more or less. In reality, we use Casimir force and van der Waals force and dispersion forces more properly, more or less interchangeably. So you're going to hear this common statement: the force is very weak, the force is very small. To me, it's an exotic force. It's an exotic manifestation of a quantum field. That's what people will tell you all the time. So in fact, there is I found here a collection of such statements. One is by Casimir himself in his paper on the Casimir effect in 1948. He says the effect is small. An experimental confirmation, may not be impossible, and it may be interesting. And of course, that Casimir was famous for understatements, and he was characteristically so there. Kleppner, the force is too weak to command great attention. Fascinating. The force is too weak. And Miloni himself, this is a tiny force. Amusingly, I mean, this never ceases to amuse me. In the New York Times in 2001, we have a report about the first papers that were being written on experimentation on Casimir forces in microelectromechanical systems. So here, Capasso and company, this is a top-notch team in the field, one of the best in the world. Capasso was at the time at Bell Labs, now Lucent, now he's at Harvard. And he was trying to show that you can use Casimir forces to actuate a microelectromechanical system. The idea was not new, but what he was doing that was new was to take a microsphere, as you can see here up at the top, and basically pump the distance between the sphere and the underlying torsion oscillator, so that the torsion oscillator would get into resonance and respond to that. So it was obviously, this is not a device that you can use, but it was a proof that you can use Casimir forces to actuate nano devices. The fact that they could do that without any trouble whatsoever attests to the fact that this force is not weak. It is actually dominant on the nanoscale. However, the New York Times reporter here, Chang, acting, I suppose, in the traditional view that these forces are weak, entitled the article in a way that I found always amusing. A tiny force of nature is stronger than thought. Well, stronger than thought by whom? It's not weak. It's actually a very strong force on the microscale. The strongest force you will find actually between neutral objects. The only force that is stronger than that on that scale would be an electromagnetic force between charged particles, but gravity is dramatically weaker than the Casimir force, on the microscale. So, but there is this tradition that you need to say that it is a very weak force, and that is why I continue to be amused when I look at articles on the gecko, our friend who is capable of walking upside down on a glass surface. We will talk about it more later at the end of the talk, but fundamentally, on the paws of the gecko, it was discovered there are about 6 million setae, filamentary structures that have evolved to interact with flat surfaces. Now, obviously, the force between each seta and that surface is very weak, but there are millions of them. And if enough of them make contact with that surface, then the gecko has absolutely no trouble walking upside down. I would like to state that one of the topics of this talk is also about fiction. There is a fiction out there that Aristotle would have been the one to first say that the gecko walks upside down, but in reality, he didn't mean that. He was not talking in that context. I mean, he was completely taken out of context, okay? And Aristotle would not have spoken about the forces between atoms and using the gecko as an example, because Aristotle was against the atomistic theory. So it's completely out of context in case you come across that mention. But more recently, people have wondered, how the gecko does it. How does the gecko do that? So there is an article by Autumn and colleagues. This one was in the American Scientist, but of course the original contributions came earlier, in which they analyzed whether this was due to atmospheric pressure, again, whether by hooks or glue or some kind of other liquid. And eventually they discovered most of the force that allows the particular gecko in question to perform this feat is due to the Casimir effect. And you can see here, a sign of the times is when The Economist talks about the Casimir effect, because the Casimir effect wouldn't ordinarily have attracted the attention of a magazine called The Economist, but in reality, at some point it did. And so here you can see a drum set in which I suppose the photographer, the artist, meant to represent here is that you can make one plate vibrate although you are in a vacuum. Now, usually a drum set would require air to vibrate, okay? And well, this one doesn't, because the Casimir force is the vector, if you want, the carrier of the force. The reason that The Economist became interested in that is that, of course, at some point, DARPA wanted to know, well, this force is creating problems, because as Feynman noticed as early as 1959, stiction is a problem. So parts that adhere to each other will not come apart. So in a microelectromechanical system, if two parts stick, you can consider the device failed. So DARPA wanted to know at some point in the early 21st century, how can we undo stiction? How can we avoid it? I think even more important, from my perspective, is how can we use this force instead of just trying to avoid it? Amusingly, again, in pursuing the idea that, let's not forget, this is a weak force, remember? It's a tiny force, remember? It's too weak to command great attention. And here we have a graduate student at Stanford climbing up sheer glass by only using Casimir forces. This actually is better than Tom Cruise in Mission Impossible when he climbs up the skyscraper in Dubai, in the famous scene in which he is almost falling off the building because the gloves ran out of battery, remember? Well, here, the uncertainty principle of quantum mechanics never runs out. And this student could go all the way up without any problem because no batteries are required. So the force is neither strong nor weak, and no batteries are necessary. So I think that this particular implementation, use if you want, you can see that I've been trying to kind of give you an idea, an abstract of what how Casimir forces have evolved from a philosophical concept to a market concept. So understandably, these particular glues, we can call them, although they're not chemical, are called gecko glues. And they are becoming probably, I would argue, one of the first products enabled by nanotechnology meeting with Casimir forces. The first product, I would say, was indeed the Johansson blocks. The Johansson blocks would have been impossible without Casimir forces. So here we have such a manifestation. Now, I would like to say that one of the most difficult things to do, and in this sense, this may explain why people talk about Casimir forces as being weak, is the fact that these forces are not weak, but they are certainly short range. So I will talk a lot about this experiment, which is one of the ones I like the best. There are several experiments that have proven the existence of Casimir forces. Remember that Casimir was a theorist, and I would like to remind you that Casimir, as we will discuss later, in 1948 was trying to explain the fact that forces in colloidal applications, if you want, didn't appear to respond as expected from the ordinary London force, van der Waals forces in the unretarded regime. But van der Waals, of course, was long dead. London didn't measure anything. He was a theorist. Casimir was a theorist. So the measurement of Casimir forces between macroscopic objects, especially in the retarded regime, was a challenge to experimental physics for decades. And there were many attempts. I will show some of these gadgets and devices over, in the course of the presentation. But the one that I find the most beautiful, and for me, it remains the most elegant today, is the one by Hunklinger. And I have spoken to him. I am preparing an article on the history of their experiment for other reasons that I will describe also in this presentation. I've spoken also to Walter Arnold, that is the last author. They were part of a team led by Dransfeld in Berlin in the 1960s and 70s that published only 2 refereed papers on this subject, but implemented a very, very fascinating way to measure the Casimir force. So here, this is an article that I wrote for the American Scientist in 2014. So the art is mine, but the idea is theirs. Hunklinger, Siegfried, told me that he was given by Dransfeld as a PhD dissertation the goal to measure the Casimir force in the most accurate way that he could. At the time, this had been done by Deryagian by means of basically scales. So you take a balance and you measure the force between 2 surfaces in a static manner by using a scale in feedback mode. Deryagian succeeded, but honestly, his error was about 100%. I mean, it was not enough to really confirm the expectations about the Casimir force behavior as a function of distance. Hunklinger told me that at some point he basically took his own Deryagian setup and threw it into the trash, and he went back to the drawing board with a new idea. And the idea was to use a microphone, something that I found genial, really. I mean, this is, in my view, a Nobel Prize caliber idea, although he hasn't yet got the Nobel Prize, but he should, really. This entire group should get it, I believe. He basically had the idea of epoxying. Keep in mind, all this was before microtechnology, before digital technologies. Okay, so we're talking about 1969 or so. And he basically epoxied a small glass disc to the membrane of a microphone. And then he assembled a spherical lens facing that disc. This lens, as you can see in the far left, attracts the small disc attached to the membrane of the microphone. Then, by taking the lens and by making it vibrate up and down, he led the microphone into resonance. Obviously, all this was done in a vacuum, so that you would have a very high Q, okay, a high quality factor. But basically, what he was trying to do, he was making a microphone respond to the quantum vacuum in the absence of any air. And this is absolutely beautiful, I think, as a way to detect this Casimir force in a dynamic fashion. In other words, he played a trick that is a classic in experimental physics by taking a static object and transforming it into a dynamical signal, which of course allows you to filter out noise, all kinds of things like that. So this was a genial approach, I think. But he went further. Walter Arnold told me, I also interviewed him, that at some point what they were trying to do was to measure the Casimir effect between different boundaries made of different materials. As I will describe later, there isn't just one equation for the Casimir force. So for instance, my students in the past semester have seen the Casimir force between ideal boundaries, but that is, the simplest case. In reality, we are not dealing ever with perfect boundaries. Casimir dealt with the perfect boundaries because that's the simplest thing to do. But if you got real boundaries, well, then it's not so simple. We will talk about the Lifshitz theory in this presentation. So what Hunklinger and colleagues were trying to do was to measure the Casimir effect between real boundaries, not just between two ideal boundaries that don't exist. So what they did then was to basically change the substance that was interacting with this small disk attached to the microphone. So maybe they had, silica, and they have silicon and other gold. They deposited gold at some point on this lens. Now, at some point, they decided to deposit a dot of amorphous silicon on the facing part of the convex, on the if you want, the apex of the convex lens that is facing the disk attached to the microphone. Now, I don't know if Walter Arnold really, means this, but he told me that at some point, as he was making the measurements, graduate students spend long hours in the lab, daytime and nighttime hours. He realized that when the neon lights in the room were on, the measurements that he was receiving for the Casimir force between these two objects was different than when the lights were off. And so that led the group to decide to aim a powerful white light into the back of the convex lens, as I described here in the center of figure. And they discovered that the Casimir force was dependent on illumination. So if you back illuminate the semiconductor, you're going to get a different force than if you do it in the condition that is at the far right. I believe that this is one of the most remarkable discoveries in the entire history of this field, because this means that we can modulate Casimir forces in time. And I believe that this is probably the first time that anybody even thought about doing it. As I will describe later, in a way, this is simple to understand. If you back illuminate a semiconductor, you're simply creating pairs of carriers, or charge carriers, and the change in the charge carrier number density causes a new contribution to the dielectric function. So in other words, the optical properties of the material change. And because the Casimir force depends on the dielectric function of the materials, you expect this force to change. So, hey, after the fact, post facto, you should have expected this. So they did a beautiful experiment in which they measured this, the Casimir force in the presence of illumination and in the absence of illumination. Now, obviously, as anybody here is thinking, you need to be very careful, because you need to, of course, make sure that the radiation pressure on the back of the lens is not causing, spurious signals. You need to make sure that the radiation re-emitted by the semiconductor is not causing a force acting on the small disk below. So there is all kinds of things that need to be ruled out, thermal effects fundamentally, which they considered. Now, I will say that the discovery was great. The only problem that remains open with the results of the, let's call it the Hunklinger, Geiselman, Arnold, Dransfield experiment, is that the effect should have been larger when you get closer, when the two boundaries get closer, whereas it got larger when the two boundaries go farther. And that is kind of confusing, really shouldn't have been like that. But it is believed that by the group that, you see, one of the great challenges of these experiments is the presence of spurious charges on the two boundaries. And because electromagnetic forces are always larger than anything, I mean, in fact, I would say that any force other than the Casimir force is larger than the Casimir force if the force is present, other than gravitation. So fundamentally, when you try to go at a large distance, which is when you would like to see the retarded Casimir effect, at that point, the presence of these charges is, dominant. So there was a problem that they had. However, the same experiment was repeated with the atomic force microphone by Mohideen and others, and they confirmed in full the expectations from theory. So I would say that if one has to be fair, the merit historically still belongs to Hunklinger and others. Now, I know that one of the reasons that I eventually became involved in the Casimir Effect was not all that. I was looking for technological applications. At the time, I was working at the Jet Propulsion Laboratory when I became aware of all these things. And as you may know, we were involved in a project called the Interstellar Probe, which was a challenge thrown at JPL from headquarters. What would it take to throw a metric ton at Alpha Centauri? I mean, can we send spacecraft to other solar systems? You know, and this was a remarkable challenge. That's how I met Robert Forward, by the way, and others eventually that I had the opportunity to meet, including Tim here, because you know we all kind of congregated around this challenge of interstellar exploration. So the reason that I became interested in that is that when we were discussing the interstellar probe, there are two strategies that we can follow. Keep in mind, we are not talking about human travel here. We are talking about sending anything, no matter how small, to a nearby solar system. So one of the strategies by making the spacecraft as small as possible. So in order to do that, you need to make the subsystems as low mass as possible. Now we know that this is the way to go because nowadays we call it the star chip, right? That's what Stephen Hawking also eventually endorsed. A microchip propelled to a nearby star system by radiation pressure. So it was the correct way to go. One of the things to do that you need to do if you want to do that is to miniaturize everything to a level that becomes unthinkable. So for instance, can we have energy storage with densities that are much higher than we have today? Can we have nanorobotics, computation, everything on a scale that is maybe 1,000 times smaller in length and larger in density? So one of my contributions to the field that I believe has stood the test of time is the idea of using the discovery by Arnold and others to design an engine cycle in which we have, this will be the bottom 4 A, B, C, D panes. We start with the 2 interacting surfaces at a large distance. We illuminate it. We allow these 2 boundaries to get closer. We let the semiconductor decay. That causes the semiconductor to go back to its original unexcited, if you want, state, and then we pull it away. So this creates this engine cycle that you can see here in the far left. I guess that the A is missing. And fundamentally, if the other side, the opposing side of the illuminated lens is charged by a positive charge, and there is a capacitor on the other side, you can use this system to convert the energy that the system has converted to increase the Casimir force field into electrostatic forces. For instance, you can recharge a battery this way. So this is very important because on the nanoscale, when you're starting to talk about nanotubes, for instance, you cannot have wires and ordinary circuits. So you need to think of another way to convert energy into mechanical energy. That's what I was looking for. Now, eventually this invention that was patented, I got about a dozen patents worldwide in the United States, Europe, Japan, and Israel, became famous for another reason that wasn't really meant to be, but because of the limitations of the theory, I believe. If the 2 boundaries are very close, and I mean closer than a nanometer, you have the appearance of energy extraction from the 0-point field. I almost took it as a joke at the time, but that idea took on a life of its own. And I want to specify clearly that at the time, I didn't think that was going to be the biggest thing to come out of this. What I wanted was a nano device that could be actuated and that could store energy by using the Casimir force. I wasn't thinking about creating energy. And I would like to stress still today, we have no experiment that does that. It remains an open question, but as I will describe later, I am, in a way, I am more interested in pushing forward towards devices that can actually use this aspect of the invention that is absolutely uncontroversial, as opposed to more controversial questions such as 0-point energy extraction, it became to be called. There is a connection from the thermodynamical standpoint with the typical four-stroke reciprocating engine that I represented up here, up on top. However, of course, in a PV diagram, orbits in the opposite direction, because in a four-stroke reciprocating engine, the gas pressure is, if you want, repulsive, whereas the Casimir force in this case is attractive, but the concept is the same. So because I see the time is going by, I will probably do what Tim says and take a few more minutes before taking questions. But I hope that it is of interest, because I want you to know that a lot of the things you are seeing have not been seen before. This is a lot of the background history of what happened. With the courtesy of Honker and Arnold, I wanted to show you some of the original photographs of the device, the instrumentation that they were using. There is an article by me that is upcoming to appear on this issue. And the whole instrumentation, unfortunately, no longer exists. There was a fire at the TU, the Technical Institute in Berlin, where this happened. And from what I understand, the fire involved radioactive materials. So they had to, when the firefighters came, they had to throw everything away, basically. So there isn't anything left. This diagram on the right is nothing but the original notes by Arnold that were eventually published in the Physical Review B. Now, let's rewind the movie so that we understand where we are. First of all, I want to stress the relationship between quantum theory and the existence of Casimir forces, because this is a big, huge issue that again goes under the heading of fiction. You're going to hear people repeat obsessively that the Casimir effect is a manifestation of the quantization of the electromagnetic field. Well, I have no doubt to tell you that I believe fully that the electromagnetic field is quantized, no doubt about it. However, the Casimir effect is not a tool to prove that that the field is quantized. People will reply to this by saying that the Casimir force and the van der Waals force have an H bar in the beginning. That proves that if H bar goes to 0, that is, if you are in the classical limit, the Casimir force doesn't exist. But this is no proof. This is a very disingenuous way to state the issue. Yeah, of course, there is an H bar as a factor of the Casimir force and the van der Waals force and the London force. But the reason is that the internal degrees of freedom of the atoms are quantized. So for instance, here you can see that Fritz London, writing in 1936, remember that London and Eisenschwitz were the ones who formulated, if you want, the first quantum theory of van der Waals forces in 1930, okay? They were not exactly the first. It was a Chinese student by the name of Chan that did it first before them, but he made an error. So they were the first to do it correctly. And so in 1930, they did that. In 1936 here, London, kind of looking back, explains the concept. And the concept here is that the molecular forces are due to the interaction between quantized atoms, a very important paper by London. Keep in mind also that London was the one who gave us the terminology of dispersion forces. Okay, we use those words to mean that these are forces that depend on the polarizability of the atoms as a function of frequency. Let me give you a quick explanation about what this means. So this is nothing but the London theory of dispersion forces in one dimension. There are many people who have done this, and another thread of my conversation on the Casimir effect that is dear to my heart is the fact that this community is very bad at citations. This causes all kinds of problems. So I would like to warn anybody who is interested that if you become interested in Casimir forces, you need to read a lot, because you will discover that these groups simply don't cite one another. It's kind of a shame, and I always call them on it. So here we have, I would say London was the one that simply said, let's take two harmonic oscillators of the type that students in undergraduate quantum mechanics study. Let's write down the electromagnetic force between these two dipoles. This is a classical force. And let's calculate the change in the eigenfrequencies of these two atoms due to the interaction of these two dipoles. This is a change that is actually to second order, because to first order there is no change. You need to go to second order. That makes that the change, if you want, in the energy of the two oscillators inversely proportional to the sixth power of the distance. Karplus and Porter in a textbook did it in one dimension. They were not even the first ones to do that. Kleppner wrote a very cute article in Physics Today with apologies to Casimir, but really he should have apologized to London, because he uses the same exact argument by London without citing London, which is bad. And Milonni did the same. So nobody cites anybody, although Milonni cites everybody. I would say that Peter was the best one from the citation standpoint. So here, look at what London says in this paper. According to quantum mechanics, are isotropic oscillators. Now that means three-dimensional harmonic oscillators, because he did it in 3 dimensions. Even in their lowest states, make a so-called zero-point motion. I would like to stress this word, because I know that sometimes people that are interested in this field get a hard time from professionals, because the word zero-point field has become a synonym with, science fiction, because, in The Incredibles, I think that there is a zero-point gun or something like that. So it's become kind of ridiculous. I would like you to know that if you use the word zero-point field, you are in the footsteps of Albert Einstein, who used it first. This was Nullpunktenergie. So it's a very reputable concept in physics to say that a harmonic oscillator in the ground state can be considered as moving, if you want, although we need to, that's a semi-classical statement, due to the zero-point field. So here we have the energy of the harmonic oscillators. So this is called the zero-point energy, obviously. So this zero-point energy is modified by the interaction between the two dipoles. That's all. There is nothing else that you need to explain the van der Waals forces. You do not need to quantize the electromagnetic field. Now, I know what people will say. They will say, well, but if you are in the retarded regime, when the atoms are very far, then you need to have the propagation of the field included in the calculation, and then the field has to be quantized. That's false. In fact, in a paper that is not very well known, in a series of papers, McLachlan in the 1960s reformulated the exact same calculation that London did, but in the framework of retarded fields, and he obtains the same exact equations that Casimir did, the Casimir-Polder force that I will discuss shortly. All this I want to say fundamentally is be careful, because it's not true that the Casimir effect proves that the field is quantized. The field can be classical. There are Casimir forces involving classical fields all the time. What needs to be quantized is the internal degrees of freedom of the polarized particles. So here it is. Here we got now an explanation circa 1930 of what's going on. You got these two particles now. So at this point, we can say we had two atoms, if you want to call them that, two three-dimensional harmonic oscillators of polarizability alpha, of ground energy h bar omega 0, and that's their distance S. Sometimes I call it S, sometimes I call it R. Apologies. So now Hamaker and others had the idea to say, let's now take two slabs, if semi-infinite slabs. So imagine this slab on the left goes on to the left to infinity, and the slab on the right goes on to infinity. And let's take all these atoms that are interacting with each other by means of the London force, and let's add up pairwise these interactions. It is not a completely trivial calculation, but it can be done. Interestingly enough, it's kind of amusing, but these calculations were first done by Newton, but they didn't know when this was done, and so it was they basically redid the calculation. They rediscovered this, if you want, and you obtain the van der Waals force in the unretarded regime that is inversely proportional to the distance to the third power. This is A, is the Hamaker constant, the physical chemistry students study. Once again, the field is not quantized. Now, what happened in the 1930s was that when they started making experiments with colloids, they discovered, and these particles were in that case spherical particles approximately, when the distance was larger, when the colloids were rarefied, if you want, well, this equation didn't hold correctly. And so that's when Casimir became involved in Eindhoven at Philips lab. So this was shortly before World War II. Just for you to believe me, this is a page from the mathematical papers of Isaac Newton. It's not in the Principia. When he did the calculation of the sum of the interactions of two spheres that are interacting with forces that are not inversely proportional to the distance squared. Can you imagine that Newton did all that without calculus? Although he had calculus, he didn't use it. He did it with geometrical methods. I mean, I think that it's shocking to imagine the mathematical genius of this man. Don't forget that Newton didn't publish his results until Robert Hooke and Edmund Halley begged him to do so when they discovered that he knew that the orbits of the planets had to be ellipses if the gravitational force is inversely proportional to the distance squared, which was 25 years after he had made the discovery. So this is, Newton's genius is just difficult to grasp, I would say. So now, as we skip into the 1930s and early 40s, Verwey and Overbeek at Eindhoven were investigating this discrepancy between the expectations from the, we can call it maybe the Hamaker theory, you know, the pairwise summation of London forces to explain the interaction of colloid particles, and the experiments, especially in the case of rarefied particles. So it was this group that had an idea, and they basically, the idea is, I mean, I'm gonna wave my hands explaining it just the way that they did. At the time, the interaction of atoms was schematically described as the interaction of radiators. So imagine that you've got two atoms that are vibrating, you know, these are harmonic oscillators, and they are at a large distance. So this electromagnetic field is propagating from an atom to the next, just the way that an antenna would communicate to another antenna. So they said, what if at a large distance, what happens is that the wave that's coming from the atom on the left reaches the atom on the right out of phase, so that the atom on the right cannot respond properly, simply because the distance is such that the vibration of the electron of the atom on the left is out of phase with the radiation coming from the atom on the right, and vice versa. So in other words, they thought that retardation would cause the two atoms to interact out of phase. Now, this is a completely classical explanation. I cannot even begin to say that this is quantum mechanical as an explanation. This is an explanation that you could actually assign as an undergraduate problem. This is an interaction of two antennae, basically, with oscillating dipoles. Now, Casimir and Polder took it from here, and in fact, they cite this intuition by Overbeek in their paper in the Physical Review, and in a later paper on Casimir-Polder forces. But then they didn't do anything to pursue it this way. They, of course, developed a genial application of an early form of quantum electrodynamics. So this, at that point, we're talking about 1948. So quantum electrodynamics did exist. And so by quantizing the electromagnetic field, they developed, Casimir and Polder developed the theory that we today call the interaction of two atoms. Now, notice that I'm referring sometimes to the Casimir force, sometimes I'm referring to the Casimir-Polder force. So more properly, we talk about the Casimir-Polder force when we talk about the interaction of two atoms. The Casimir force is the interaction of two macroscopic, perfectly conducting boundaries. I would like to say that from that point forward, much happened. So for instance, there is this fascinating discovery by Edward Teller, the same Teller of the atom bomb, the hydrogen bomb, that, if we take now the idea of London of two harmonic oscillators in the unretarded regime, and we put 3 of them instead of 2, you discover that it depends on how you place them. If you got 3 at right angle, it becomes a repulsive force. So this was the first time that people discovered that dispersion forces can be repulsive. This was very early, 1943. This was before Casimir even came on the scene. And there is another very nice article in the American Journal of Physics by Farina and others on this issue in 1999 that you may want to look at. So when Casimir and Polder came out, eventually discovered the Casimir-Polder interaction, something that happened was that, as you will see shortly, the equation is dramatically simple. Instead of being a potential that decreases as the distance to the 6th power, it is a simple equation with the distance to the 7th power. And so they wanted to understand how this could simply be due to something uncomplicated, but they were unable to find an uncomplicated explanation. In fact, I will tell you that there is a subfield of Casimir force research that has got to do with deriving a simpler explanation of the Casimir-Polder force and other, So what is the simplest thing that we can do and get the result? I would say in my book, McLachlan wins the prize, but that's an argument of taste, obviously. The reason that I believe he does is that he doesn't quantize the electromagnetic field in doing it. So this is kind of a violent summary of everything that happens. I will just provide the references here. I would say that Spruck did a fantastic job at explaining why 2 atoms that are in the retarded regime are expected to interact. And so basically he told us this, now I would like you to understand what's happening that is very different than before. This is now, keep in mind, this is 1978, 1986 even. So now we are acting under the effect of a well-developed quantum electrodynamic theory of the electromagnetic field. So now the field has become an independent quantity. So here, Spruck says, we got 2 atoms at a distance, 2 quantized atoms, obviously, with dipole moments mu1 and mu2, but now they are immersed into this quantized field. We call it the 0-point field without any further shame about it. And he says, okay, he first deals with an equation that you can find this article in the Physics Today, that's easy to find. He obtains a potential interaction between these 2 between these 2 atoms that is only due to the existence of this classical field. And in fact, Spruck jokes there. He says this is a result that Maxwell could have derived and perhaps did. But Maxwell didn't, because Maxwell didn't even have a fully developed atomic theory. Certainly, Maxwell never schematically described the atoms as dipoles. That was done later, so by a few years, I would say. So, but then by quantizing the electromagnetic field rapidly, Spruck derives an equation in which the Casimir-Polder force is inversely proportional to the potential, to the distance to the 7th power, and the product of the 2 polarizabilities. The correct factor is 23/4 pi, a great mystery. By the way, I think the Casimir was on vacation in Sicily when he was reached by the first confirmation that his result was correct. This is a very famous little episode in the history of the Casimir Polder force. Now, what the question now is, Casimir went back independently than Polder and said, okay, now imagine that we have two boundaries now, macroscopic boundaries, and we want to know, before Tim becomes worried, I am shooting, I promise to be done at the half hour, okay? I promise. I'm accelerating. So two perfectly reflecting boundaries. And Casimir said, now, what about the interaction of these two? So this is an interesting problem, because if the boundaries are perfectly reflecting, then the constituent matter of the boundaries no longer matters. The only thing that matters is the field. And Casimir, in a later paper, described this as poor man's quantum electrodynamics, poor man's QED. In other words, he says, the only modes of oscillation that are possible between the plates are the ones that bring the field to zero at the boundary because of the typical boundary conditions of the electromagnetic field. He then calculates the energy between the plates, the energy outside of the plates, and the change between having the plates and not having the plates, technically speaking, is a difference between two infinite quantities. And then Casimir does something that we've become familiar with. He takes the difference of those two infinite quantities. Today, we call it renormalization. Some of you who are familiar with the history and philosophy of science may know the name of Feyerabend, who was laughed openly at quantum electrodynamics for the concept of renormalization. He stated in a famous correspondence with the famous physicists of the time that QED was a theory in which you first know the answer, and then you take the difference between two infinite quantities and you obtain exactly that. And there was a debate, but he never was convinced of renormalization as an appropriate way to extract quantities from the theory. Well, Casimir did that. And so by renormalizing, he obtained the correct answer. I would like to say that there is an ongoing debate even today as to whether the Casimir force is intuitive or not. Milonni falls on the side that the force is intuitive, in the sense that he says, what do you expect? Once the two atoms are interacting, a slab made of atoms, two slabs made of atoms will attract. On the other hand, another Nobel Prize winner, right, Julian Schwinger, who got the Nobel Prize with Feynman and Tomonaga, states that it is one of the least intuitive consequences of QED. So Schwinger said, you know, we got two boundaries here whose structure doesn't matter because they are perfectly conducting and they happen to attract. How that would happen to Schwinger is something just short of a mystery. For Milonni, instead, Milonni says something else. Milonni says, well, okay, let's look at it. Let's take two slabs made of such atoms. These two slabs are not ideal, but then by using a very famous relationship in which the polarizability of the two atoms, you know, this is called the Lorentz relationship when the functions are dependent on frequency, down here at the bottom left. This is the connection between the dielectric function and the polarizability of the atoms. You can connect the polarizability of the atom in the Casimir-Polder equation to the dielectric function of the two boundaries. Finally, by taking the dielectric function and sending it to infinity, as you would in a perfectly conducting boundary, you obtain an equation that is wrong, but not by much, by about 30%. So Milonni says, so it's not so strange, considering the fact that Casimir-Polder forces are not additive, as discovered by Teller. It's not so surprising that the Casimir effect exists. So I tend to agree with Milonni personally, that there is no mystery here. And let's not forget that the Casimir limit is unrealistic. The fact that the Casimir-Polder force, the Casimir force, it's an interesting mathematical problem, but you cannot have perfectly conducting surfaces. So the lack of intuition that Schwinger complains about is not so critical to me. But I do understand that we teach children that conducting surfaces that are neutral do not attract, neither attract nor repel. And now children need to be told that they attract if these two surfaces are parallel to each other and parallel plane surfaces. There is a different way to look at it. I mean, this is kind of the Casimir way, if you want. So this is from Power's beautiful booklet on quantum electrodynamics from the 1960s, in which he basically says, hey, let's just calculate the 0-point energy inside the boundaries, and you know, by again extracting. But there is something else that he does instead of renormalizing. I mean, in a way, Power does renormalize, but what he says he does, he introduces a cutoff, and this is a cutoff that is completely arbitrary. But you know, it's I mean, at this point we are trying to extract the Casimir effect from mathematics in 4 lines. That's not easy, because it's not something you need to say. It is that this is not a simple effect to really calculate. Now, I would like to explain that Milani, in his attempt to make it even more natural, came up with a very provocative explanation that I always liked. This is very cute to find in the literature with Cook and Gauguin. Milani wasn't technically the first to discover this, but he certainly was the most famous to publish it. So basically he says, let's imagine that we got 2 boundaries that are perfectly conducting. And now we got, if we want to put ourselves inside of the framework of quantum electrodynamics, we're going to have virtual photons of the 0-point field. Well, these photons will bounce around, right? And we have boundary conditions on these photons, in that only some frequencies are allowed within the gap and all frequencies are allowed outside the gap. So if you are inside the gap, you're going to write the radiation pressure. This is a classical equation for the radiation pressure due to the virtual photons inside the gap. So that pressure is pushing the plates apart. But then you have, of course, the force due to the outside of the plates pushing from the left on the left plate and from the right on the pushing towards the right on the left plate and on the left on the right plate, and that force is due to all modes that are possibly allowed. Now, obviously, these 2 pressures are both infinite. So once again, you got to renormalize, and this leads you to a nice, beautiful problem with the Bernoulli numbers. There is this equation here at the bottom, a beautiful mathematical problem that was there is a very nice article by Jonathan Dowling that really, in a fun way, describes this calculation in a way that is very entertaining. Unfortunately, Jonathan died untimely a couple of years ago, but I mean, a beautiful paper that you may want to find by Jonathan Dowling on the Casimir effect. I think it's in the Mathematical Journal. So anyway, once again, it's a form of renormalization, if you want. Now, this is the closing of the article by Casimir in a very difficult to find journal, I would like to say, but it's out there, a Dutch paper. And what I would like to say, just again, to be provocative regarding the issue of quantized fields, going back to Casimir, to Milani, please notice that the field doesn't have to be quantized for this to happen, okay? You can have any field, including a stochastic field, that happens to have the energy of a quantum field, and you're gonna have the same effect. Probably the best demonstration that this is true is the acoustic Casimir effect. This was introduced by La Raza and others years ago. And basically you take 2 plates, you put them inside of a tank, and you make a lot of noise. And these 2 plates will interact. Again, you got radiation pressure coming from the left and from the gap. And depending on the spectra, the spectral noise of you establish inside of that tank, you can engineer this force in any way you want. One of my students, an undergraduate student working with me when he was at Robert Morris University, and I was in Saudi Arabia at the time at Jazan University, he built this the same gadget, and he was able to obtain repulsive Casimir forces by, as I say, acting on the spectrum of the noise in the tank. You can actually hear the noise and see the plates move. It's quite remarkable. Now, in the electrodynamical case, you cannot do that for the simple reason that the electrodynamical forces, the spectrum of the zero-point field is determined on Lorentz invariance considerations. It cannot be changed. You can change it by introducing real photons, but you cannot engineer the vacuum in that way because you will be violating Lorentz invariance. As we approach the close here, I know that this is a lot of stuff and I will accelerate towards the end, but I would like to say that post Casimir and Polder, the field was at in a way at an impasse, because now you got the real boundary case. Right? We have the Casimir-Polder interaction, which is an interaction between the two actual atoms, if you know the polarizability. And then you have this very idealized case, which is the idealized case of two boundaries that cannot exist, perfectly conducting. What do you do if you have two boundaries that are made of real materials, like two pieces of glass, to give you an example? This was a problem that went unsolved for a long time, and I mean a few years, until Evgeny Lifshitz in Russia, in the Soviet Union, formulated the theory that we still today call the Lifshitz theory. This Lifshitz theory was a complete stroke of genius. I mean, it is a remarkable accomplishment in any sense. Not an easy piece to digest, but genial, because Lifshitz was able to, basically what he did was a semi-class. Again, I think some of the things that you see with the geniuses of physics is how they cheat the rules of the game. Because if you had wanted to do this right, you would have had to apply quantum physics to a solid and obtain the Casimir force, the Lifshitz theory that way. But that cannot be done. Even today, we have difficulty to do that. So what Lifshitz did, he basically recycled a device by Ritov, in which he injected noise inside of the solid and wrote down the properties of the interaction of two slabs starting from this semi-classical noise. I mean, he doesn't start from the commutators of quantum electrodynamics, to give you an example. So technically speaking, this theory has always puzzled theorists because it's not a fully quantum theory of Casimir, of the Casimir force, but it works fine. It is the most modern theory that we still have today. So I'm not going to go through that because that would require another seminar by itself. I just want to say that the closing here, I reproduce the equations from my paper. This is not what, I didn't do this. Lifshitz did. The only thing I'm just citing this paper because you can find these equations written in terms of this Lifshitz integral. I just want to tell you, it's not a friendly integral to calculate because it goes into 2 dimensions to infinity. So it is an improper integral in 4 different places. And in fact, you might wonder, how did Lifshitz calculate it in 1955? I use Mathematica to do this. Okay, how did he do it? Well, Lifshitz had the genius. It really required a deep knowledge of physics and a mathematical sensibility that is uncommon. He realized that the dielectric function on causality considerations, if calculated on the imaginary axis, becomes a real function. This is due to the Kramers-Kronig relationships. I repeat, the dielectric function, which would cause any solution to the Lifshitz theory to be impossible to calculate, become a piece of cake if you just realize that you can transform the integral from the real frequency axis to the imaginary frequency axis. Because if you do that, the dielectric function calculated on the imaginary axis is a real function. So it is pretty amazing. And eventually he was able to tame that monster. And the only thing that he didn't have was the dielectric function for real materials. And we have been accumulating knowledge on this calculation ever since, fundamentally. But you can do this calculation today. I want to state that, especially if the slab is of finite thickness, even Mathematica, even with parallel computing, this is not a trivial calculation. It takes some time for a machine to do these things. At the end of the day, what you get is something that looks like this. Again, this is from my paper cited before. If you are at a large distance, the Casimir force decays inversely proportional to the distance to the fourth power. As you get closer, it decays inversely proportional to the distance cubed. So here, somewhere in the middle, you got the transition from unretarded to retarded regime. What's very interesting, philosophically speaking, is that you got 5 here, but I mean, there are more theories that lead to the same equations. What does that mean? I mean, the bad news is that the Casimir effect is not an effect that allows you to discriminate amongst any of those theories, because they all give you the same equations. It's a very robust conclusion, but it doesn't even depend on whether the field is quantized or not. So you can find it, it's proportional to h bar, but unlike what they will tell you, not because the field is quantized, but it's because the atoms are quantized. In fact, Lamoureux, who was the first in modern times to measure the Casimir effect, by using, Steve told me, I interviewed him at Yale, by grabbing stuff literally from the store, he and another student measured this Casimir effect in 1996, I believe, to within about 5%. Later, he downgraded himself to 30%. There was a furious debate with the Russian school. I mean, this goes under the heading of these terrible debates inside of the Casimir force community. But at any rate, Lamoureux eventually states here very clearly in Physics Today that photons, it's not to say the photons don't exist, but that experimental proof for the quantization of the electromagnetic field must be sought elsewhere. Nobody doubts that the electromagnetic field is quantized. Now, the reason that I want to state this very clearly is that there was a paper more recently by Kwak and others in Physical Review Letters stating that if a gravitational Casimir effect were to exist, that would resolve the problem of gravity quantization. That's false. You can very well have a gravitational Casimir force with a completely gravitational gravitational force. And I mean, you can have general relativity that has got the field as classical, not quantized, and still have a Casimir force that is gravitational. And I have proved this in a paper in symmetry that is, you can find that open source published by Jordan McClay last year. I'm gonna run through the rest of it here. This is the Deryagian experimentation with the scales, balances, 1960. State of the art in 1960 with an error of about 100% plus or minus. This is the paper by Kwak in Physical Review Letters, in which he also made a computational error that I corrected. It was a battle. The Physical Review Letters didn't want to even admit that the computation was incorrect by a factor of 2 pi. But bottom line is, interesting idea. But remember, even if the gravitational Casimir force is detected, that does not prove that the gravitational field is quantized. We don't have the time to get into it, but I want to say that this is, in my opinion, one of the most remarkable final frontiers for the Casimir effect is its application to Casimir forces. Any field to gravitational fields, any field that has got fluctuations eventually any field between interacting fluctuating oscillators will contribute a Casimir force. I would like to say that from the numerical standpoint, so far, I have only spoken about the archetypal geometry of parallel planes, but obviously this is not the case. So I published a paper that was some kind of a generalization or well, let's call it a simplification actually of the imaginary frequency green function method introduced by Rodriguez and others at MIT. They used FDTD. I showed that it can be done with ordinary FD, finite differencing. But it's a long calculation when the boundaries are not parallel plane. It can be done today. Once again, you don't have to quantize the field. In fact, it's kind of interesting because Rodriguez and others and I only use the machinery of classical electromagnetics to do it. I wanted to close a second with a funny subject here. That is one of the myths. There are several. You're gonna hear people tell you that ships at sea attract due to the Casimir effect. So if you got two ships in the ocean, they attract. This is a very widespread myth that you're going to find in the literature. And I would like to say that you need to really be careful. This is just not true. There was a debate between me and the author of this paper. I basically was fascinated because in the American Journal of Physics, Boersma published a paper in which he says, if ships are atoms and you put them into a wavy sea, then you're going to have a Casimir force corresponding to their attraction. Now, this is a very legitimate question. In fact, I believe that that is true, that if you can put, two plates in a tank and you make waves in that tank, you're going to have a Casimir effect due to these waves inside of that tank. But then Boersma went to an old book about navigation from Causet in the 1800s. And he published this figure in which he says that two ships attract each other if placed in a storm, in a stormy sea when the wind has abated. I was absolutely driven by curiosity. I mean, this was an amazing book, very difficult to find. Eventually, I found the book in a bookstore in Australia. I ordered it online. And what I found shocked me because what I found is the opposite. So this is the French. I'm not going to try to read it because my French is not good. But basically, the French doesn't say that two ships attract in that condition. The caption at the bottom is not the correct caption. The caption at the bottom that Boersma took came from this one. It says in here that two ships attract each other in flat calm, not when the sea is rough. When the sea is rough, in fact, the book warns sailors to stay apart from another ship simply because their riggings may become entangled. It's got nothing to do with any force. It is in this situation that the two ships seem to attract. It's got nothing to do with waves, which completely invalidates the argument. So I wrote to the editor of the American Journal of Physics, and I said that this, basically, despite the physics, it's unethical that the two captions were switched. And the American Journal of Physics refused to publish any comment on that. And so it ended up to Nature. Nature was the one that kind of embarrassed everybody, because Nature likes to do these things. So you're going to find a paper by Physics Ball, kind of a funny one, entitled "Popular Physics Myth is All at Sea." So there are several of these that I've spoken about today. Be careful when you analyze Casimir forces. Don't believe everything you read, because sometimes people just want to push a story, and I've given you a few today. In closing, I would like to say, I'm really accelerating, I promise, Casimir forces in microelectromechanical systems. This is what we've covered with my students this semester. Jordan McClay was the one that put the two together, although we need to not forget that a great genius of physics, I think, Robert Forward, who unfortunately left us too soon to brain cancer, was the first one that really understood the interaction of energy and electrostatic energy and Casimir forces by introducing something that looks like a battery, basically, a Casimir force battery. In his implementation, it cannot work, but he showed that also the numbers are not interesting. But conceptually, it was the first time that he showed that the Casimir force and electrostatic forces can exchange energy. Okay, that's what fascinating. Jordan McClay was the first to show that microelectromechanical systems are heavily affected by Casimir forces. So we are talking about the early 1980s. In his system, energy is conserved. There is no friction. There is no outside resonance or anything like that. But this was the paper that Capasso and others used as a guide in their experimentation. So I think that Jordan McClay must be credited with the idea to put the word Casimir force and the word microelectromechanical system in the same sentence. We are kind of going towards the end here. I want to say that we have spoken about the physics a lot, okay? But let's not forget that now we're talking about the marketplace. And as you all know, I think that Elon Musk has got the story that it takes a lot of energy to transform a good idea, a rocket in his case, into something that can revolutionize the market. I'm not talking revolutionizing physics, because rockets still fly for the same reason. So the Casimir force solution, let's call it that, I am pursuing it personally now from academia, because it became just impossible to do it from inside of the marketplace, because the time horizon of 20, 25 years is unrealistic. I'm very happy to see that the Gecko Glue group is now getting to the point that they are making products that are being marketed. But remember that when I said the word Casimir force at JPL, it wasn't well received. Now it's considered obvious that the Casimir force is an application for adhesion. But at the time, it wasn't very reputable. In part of it also, I believe that the Casimir force community of enthusiasts embraced fiction, and that didn't give us a good name. So we need to be careful that we stay to the physics that is demonstrated in the laboratory without taking unnecessary leaps. You can revolutionize the market without leaping anywhere, fundamentally. I would like to state that among my more recent contributions, I have proposed a particle accelerator in which the particle that is being accelerated is a core of a nanotube. And this is an alternate, this is a section that repeats itself for thousands of times. And so by illuminating the different sections of a nanotube and using the same strategy that we've described before, you can accelerate this core and expel it at super high speed. I promised Tim some propulsion idea. So this is one. You can take a core and expel it at tens of thousands of kilometers per second, much higher speeds than with ion propulsion engines. And if you can create a carpet of these nanotubes that are sucking nanoparticles and accelerating them, provided that you can provide the energy, you can get thrusts that are at the level of chemical engines while having specific impulses proper of ion propulsion engines. And I presented this at the Joint Propulsion Conference of the AIAA a few years back, well, almost a decade ago. I would like also to say that I published and at some point patented a system in which energy, electrostatic energy is stored, again, by using the nanotubes as a strategy. So this is a way to use the forward idea of simultaneous interaction, electrostatic interaction and carbon nanotubes, along with the fact that nanotubes allow you a form factor that is much higher. And I would like you to start to see that, you know, we got astronauts here. This is in the Vomit Comet, grappling objects by means of the Gecko Glue. So it's going to space. In fact, I've seen there are two small robots now in the International Space Station that grapple to their charging stations by means of Gecko Glue. The Gecko Glue is one of these applications that I would say, you know, shows that the Casimir force is going to space. There is another one that is less known, and that is a transistor, if you want, that again would require too much to talk about, but basically transistors introduced by Rooks and others, the company is Nantero, in which interacting carbon nanotubes touching each other and sticking by the Casimir force create, you know, zeros and ones, and that's flown in the space shuttle already. So this will be a transistor that doesn't require semiconductors. I'm getting to the end here. This takes us back to the table that I showed you at the beginning. A lot of stuff that can be pursued. And I would like to again encourage anybody who gets into the field to understand that, yeah, new physics may very well happen. It will happen. I'm enthusiastic about it. my interest in the breakthrough stuff is on the fundamental structure of space-time. So I look forward to discoveries in that field. But I would like you to understand that, again, going back to Elon Musk, it is the transition from what we know to the marketplace that is the battlefield for Casimir Force research right now. And it takes a lot of work, even to make a new battery based on Casimir forces. I have presented in Silicon Valley dozens of times to people who, including Nobel Prize winners, who never had any doubts that I was right. The question is the market strategy. So that is where the battle is really happening right now. So I will stop here and thank you for your patience. I apologize for going over. So best wishes from beautiful Izmir, Turkey. This is one of the most beautiful places in the world. I hope that you will visit someday. Thank you, Tim, for your patience.
Well, thank you, sir. So let me do this. Let me see. Let me stop your screen share. And I want to put this on gallery view. And everyone, please give an enormous applause for Dr. Fabrizio Pinto. Sir, I think you may be the world's leading expert on Casimir Force. If not, you are certainly one of the world's leading experts. So thank you so much. Thank you so much for presenting on this.
My pleasure. My pleasure.
And then you have the focus on propulsion as well. So I mean, this is, you know, you have a really novel specialization and you're applying that towards, you know, breakthrough propulsion, which is just an incredible combination. So thank you, sir.
Thank you.